All right, my friends, it says the function f is twice differentiable for x values that are greater than 0, with f of 1 equaling 15 and f double prime of 1 equaling 20. Values for f prime, the derivative of f, are given for selected values of x in the table above. For part A, they want us to write an equation for the tangent line to the graph of f at x equals 1, and they want us to use this line to approximate f of 1.4. Okay, so let's get started. So for part A, I'm going to go ahead and just use the idea of point slope here. And then it looks like I know that the graph of f hits the point 115. And I can figure out from the table that f prime of 1 is 8. So I'll just put that information in. So y minus 15 equals 8 times x minus 1. And that's the first thing they asked us for. And then they asked us to approximate f of 1.4. So we will just add the 15 over. And y, when x is 1.4, would simply be 15 plus 8 times 1.4 minus 1. 1.4 minus 1 is 0.4. Multiply it by 8. I think you get 3.2. So it looks like we're getting 18.2. And then, just to save myself a little writing, I'm just going to say that f of 1.4 is approximately 18.2. There we go. That's part A. Now for part B, use a midpoint Riemann sum with two subintervals of equal length and values from the table to approximate the integral from 1 to 1.4 of f prime of x dx. They want you to use the approximation for that to estimate the value of f of 1.4 and show the computations that lead to the answer. So for something like part B, if you get thrown off by tables, you could always graph the information that you're given here. So let's say, here's 1, and then 1.1, 2, 0.3, 1.4. And then I'm just going to graph the graph of f prime. So let's see, put 1 in, you get 8 out. Let's see, we'll just do 8, 10, 12. Oh, not going to win any awards on this one. Anyway, and there's 14. So put 1 in, get 8 out. 1.1 in, we're getting 10. 12, we're getting, or 1.2, that is, we're getting 12 out. 1.3, we're getting 13 out. And 1.4, we're getting 14.5 out. Something like that. So there's probably some smooth continuous curve that plots these points that we will never know all about, but it probably exists. And so the integral from 1 to 1.4 of f prime of x dx. Since we'll never know, what f, let's say f prime looks, let's say f prime looks like this, you're approximating the area of whatever that exact curve would look like. And they're asking you to use a midpoint Riemann sum with two subintervals of equal length. So I'd split 1 to 1.4 into 1 to 1.2 and 1.2 to 1.4. Midpoint sum means that to get the height, you plug in the midpoint of the subinterval. So plug in 1.1, and then that would be the height of that first rectangle. Plug in 1.3, and that would be the height of the second rectangle. That's midpoint sum with two equal subintervals there. And so we would say that the area under the curve on the interval from 1 to 1.4, under the curve of f prime, would be approximately, let's see, so the base of each of these looks like it is 0.2. And then you'd multiply 0.2 times the height of the first rectangle, which would be 10 here. And then you would multiply that base 0.2 into the height at 1.3, which would be 13. Oops. There we go. So 10 plus 13, 23 times 1/5, so 23 over 5, I suppose. or any way you want to express that. So I would say the integral from 1 to 1.4 of f prime of x dx is approximately 23 over 5. There we go. Now it says to use that approximation to estimate the value of f of 1.4. So I would start by interpreting the integral that we were given using the fundamental theorem of calculus. So if you find the antiderivative of f prime, you would get f, and then you'd plug in the upper bound to it, and you would plug in the lower bound into it and evaluate. And so this integral on the left side, that is that approximately 23 over 5 deal that I found. And f of 1.4 is what we are approximating. And f of 1 was given to us in the original write-up as 15. So I would just add the 15 to both sides to get my approximation for f of 1.4. So it would be 15 plus, I don't know, 23 over 5. What is that? 4 and 3/5. So I would get that f of 1.4 is approximately 19.6, I suppose, or 3/5 or whatever. There we go. All right. Moving on to part C. Part C says to use Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 1.4 and show the computations, not complications, that lead to your answer. So getting started, they want us to start at x equals 1. So round 1 is just finding the equation of the tangent line at x equals 1, which we had actually already done in part A. So you could use your work to here. So I would just say y is equal to 15 plus 8 times x minus 1. So that was the equation of the tangent line at x equals 1. And then we're trying to get from x equals 1 to 1.4 using 2 steps of equal size. So that means that if we need to go from 1 to 1.4, that's a total distance of 0.4. Split that into 2 equal parts, and you're going to add 0.2. So this was at x equals 1, and so we're going to plug in 1.2 to that. There we go. And what do we find out? We find out that f of 1.2 would be approximately what we're about to get here. So 0.2 minus 1 is 0.2 times 8, 1.6 plus 15, 16.6. All right, round 2. All right, round 2 is when you would use this number, the 1.2 and 16.6, as your point of tangency, and then you just need to know the slope of the tangent line. And so I'll just write it down here. So we also need to know what f prime of 1.2 is. So let's see, where could we get that information? Oh, right here. So f of 1.2 according to the table is 12. So I would have y minus 16.6 is equal to 12 times x minus 1.2. There we go. And then add the 16.6 over. There we go. And then last thing we plugged in was 1.2. Step size of 0.2 would get us to 1.4. Just plugging 1.4 into that line equation. And then this left side would be an approximation for f of 1.4. Make sure you use approximately equal to signs there. And so let's see, 1.4 minus 1.2 is 0.2. Multiply it by 12, we get 1.6. Add it to 16.6, we get, I believe, 18.2. So Euler's method would say that f of 1.4 is approximately 18.2. Lots of ways to approximate f of 1.4. All right, now moving on to part D. Part D says write the second degree Taylor polynomial for f centered at x equals 1 use the Taylor polynomial to approximate f of 1.4. Okay, so for part D, I'm going to show the plan first. A function, this function will be approximated. And I think it said it's centering it at 1. So f of 1 plus f prime of 1 times the quantity x minus 1 plus f double prime of 1 over 2, or 2 factorial, same thing, times x minus 1 squared. It said second degree, right? Yes, second degree. Okay. So this is the second degree Taylor polynomial for the function x centered at x equals 1. And so the idea is if they connect at 1, that they won't be too far apart if you don't go too far away from 1. So f of 1.4 would be approximately, let's see, f of 1. What's f of 1? I'm sure I should remember by now. I think it's 15. Okay, f of 1 is 15. I believe f prime of 1 was 8. Wait, I should actually, let me just back up a little bit. Let's just keep this in terms of x. F prime of 1 was 8. F double prime of 1, they also gave you 20. Like so, and 20 over 2 is 10. So I'm just going to erase that, put 10. There we go. Okay, so now f of 1.4 would be approximately just that with 1.4 put in for all the x's. There we go. So you got 15 plus 1.4 minus 1.4 times 8, 3.2. Same thing, 1.4 minus 1 is 0.4. Square it, you get, I believe, 4 tenths times 4 tenths is 16 over 100. Oh, 0.16. Okay. All right. So 10 times 0.16 would be 1.6. There we go. Okay, so then add all this up, 1819.8. There we go. And I do think that that's everything. Yep. There we go. I think that's everything. I'll let you check the scoring guidelines to see what your base score would have been, but hopefully this makes sense. Take care, everybody.